All right, good morning, Algebra 2. This is section 7.2, day 1 notes. We're talking about rational function graphs, and today we're focusing on holes and vertical asymptotes. I always almost want to cuss with that one. Okay, so first things first, what the heck is a rational function? A rational function is a function that can be written as a fraction. So f of x is equal to p of x over q of x, where p and q are polynomial functions. So like x squared plus 2 or 3x plus 4x squared functions. But your bottom, your q of x, it can't equal 0, okay? The reason why it can't equal 0 is because we can't divide by 0. That's not a thing. If you try to do 3 divided by 0 in your calculator, it gives you an error. So basically, a rational function is a fractional function. Okay, so it's just another fancy word for fractional. Now, a point of discontinuity, okay, fancy word, discontinuity, is a place where the function or your equation cannot exist. It's where you would end up dividing by 0. So what's going to happen is you're going to set your denominator or the bottom of your fraction equal to 0 and solve. Okay, we've done this before. So examples 1 through 3, we're going to find all points of discontinuity. So first things first, we have 1 over x squared plus 2x plus 1. Well, first things first, we have to do your guys' favorite thing. We got to factor. Okay, so we have to take this x squared plus 2x plus 1 and factor it. And I've done that work down here. You take your back number and put it on top. And again, remember, that is what you are trying to multiply to. And then your middle number, which is a positive 2x, that's what you're trying to add to. So you're trying to figure out the multiple or the factors of 1, stuff that multiplies to 1 that ends up adding to 2. So the only stuff that multiplies to 1 is 1 times 1. So those are our factors, 1 and 1. So when we rewrite this, all of my factoring today I'm going to do in gray. Okay, you should be pretty confident in this by now in your young lives. Okay, we've been factoring for what feels like forever now. So this gives us 1 over, and since we have a lead 1, this imaginary lead 1, we can just write this as x plus 1 times x plus 1. Where did I get those 1s that I have? I got them from here. Okay, so now finding points of discontinuity means that we are going to take our denominator stuff, or stuff in the bottom of your fraction, and set it equal to 0. So we have x plus 1 times x plus 1. We set that equal to 0. And now we set both of the parentheses equal to 0. We've done this before. But we have 2 of them. Do we want to write x plus 1 times x plus 1 equals 0 and x plus 1 equals 0 twice? No, we're lazy daisies, right? So solve for your x. Subtract 1. X is equal to negative 1. So our point of discontinuity, and I'm going to abbreviate this, discont, is at x is equal to negative 1. Okay, so what you solve for your bottom of your fraction, that's going to be your point of discontinuity. Okay, all right, if you want to rewatch this, absolutely. Oh, we got Christmas colors happening. Okay, for number 2, we have 1 over x squared minus 16. Well, first things first, I know x squared is a perfect square, and I know 16 is a perfect square, and there's a minus sign in between. So that means we're going to be using difference of squares. So x squared is the perfect square of x. 16 is the perfect square of 4. There's a minus sign. That's what you need for the difference of squares. You need to have a minus sign. If it's a plus, it doesn't work. So we have 1 over x plus 4 times x minus 4. Difference of squares. We used this main function that we use, this equation for difference of squares here at the bottom. Okay, my a value was x, my b value was 4. So you have x plus 4, x minus 4. Now, again, find points. We're going to find points of discontinuity. So we're going to set the bottom equal to 0. So we have x plus 4 times x minus 4 is equal to 0. We set both parentheses equal to 0, so we get x plus 4 equals 0, x minus 4 equals 0. Solve for both, and I'm going to do this quick. We get x is equal to negative 4, x is equal to positive 4. So our points of discontinuity are these two values that we found. X equals plus or minus 4. I'm going to shorthand it. Positive 4 and negative 4. And that's your answer. I'm trying to make this video a little short. Not super long for you guys. Okay, now we have x squared minus 1 over x squared plus 2. Okay, so we have to check. When you have two terms, you always want to check to see if it's a difference of squares or the sum or difference of cubes. Well, x squared is a perfect squared, but is this 2 a perfect squared? No, so we can't factor. But we still need to set it equal to 0. So we're going to set it equal to 0, and we have x squared plus 2 is equal to 0. Subtract 2 on both sides, we get x squared is equal to negative 2. Now in order to get rid of a square, remember we got a square root on both sides. X equals, well, when we square root a negative, what was that thing that I always asked you to pull out? You had to pull out i's. So what happens here is you have plus or minus I root 2. But we can't have imaginary numbers. This isn't real. It's not real. It's imaginary. Okay, so we can't factor, and it'll never be set equal to 0. There will never be a 0 at the bottom of your fraction here, so that means there are no points of discontinuity. Okay, imaginary numbers, not real. We don't use those, okay? Once you see that you're getting an imaginary number, no points of discontinuity. All right. Now, there are different types of discontinuity, okay? There's holes and there's vertical asymptotes. Now, what a hole will look like on a graph, okay, what a hole will look like on the graph, it is going to be super confusing. Are you ready for this? You have your graph, there's a big hole in your graph, okay? So, a hole is a hole in the graph. So, this means it's a gap in your function, a hole in your graph, Wow, don't know how to type. Now, this happens in an equation when a factor is on the top and bottom of the fraction. So when a factor is on the top and the bottom of a fraction. Now, a vertical asymptote, okay, which I'm just going to start calling VAs so I don't accidentally cuss at you, is a dashed vertical line that the function or graph gets close to but never touches. So if I have this graph here, it's going to get close to this dashed line, but it'll never touch, okay? No touching. Now this happens in an equation when the factor is in the bottom of the fraction, or when a factor is on the bottom of the fraction, but not on the top, okay? So whole has to be on the top and the bottom. VA is only on the bottom, okay? Whole, top and bottom, vertical asymptote, only the bottom. See, almost cussed there. All right, now if a whole and a VA are at the same point, you're only going to state it as a VA, okay? All right, so let's go through some examples so you know what the heck I'm trying to tell you. So number 4, we have x plus 3 over x plus 3 times x plus 7, and this is supposed to have a parentheses here. Now, we have x plus 3 on the top and on the bottom, okay? So that means if we set that equal to 0, we're going to have a hole at x equals negative 3. So you're just going to do the opposite sign. That's a quick way to do it. You just do the opposite signs. Now we have one on the top and one on the bottom. That's why it's a hole. Now we only have x plus 7 on the bottom. So that means it's going to be a VA. And if it's a positive 7 here, when we set it equal to 0, it becomes a negative 7. Okay? All right. Now, number 5, we have x plus 5 on top, then we have an x plus 5 on the bottom, another x plus 5 on the bottom, and an x equals negative 2. So, we have a hole at x plus 5, but then we also have a VA at x plus 5. So this is where that little love note I wrote, if a whole and a VA are at the same point, so in this case they're both at x equals negative 5, because if we set this equal to 0, it becomes x equals negative 5, you only state it as a vertical asymptote. Ooh, okay, so that means it's going to be stated as VA at x equals negative 5. So basically, if you see, okay, pay attention, if you see you have one of those factors on the top and two of them at the bottom, you're going to state it as a VA. Okay, but if you have one on the top and one at the bottom, it's a whole. One on the top and two at the bottom, it's a VA. Okay, and then we have one more. We have this x minus 2. If we set that equal to 0, that means we have a VA at x equals 2. Remember, opposite signs. All right, and there's only one at the bottom. It's only at the bottom. There's nothing up top, so that's why it is a VA. Okay, looking at 6. Let's use a different color here. We have x times x minus 1 times x minus 4 on the top, and then we have x times x plus 1 at the bottom. Well, we have an x on the top and an x at the bottom. So we know this is going to be a whole at, now if we set x equals to 0, we can't do anything with that. So that means we have a whole at x equals 0. We have no other wholes happening, but we do have a VA. We have this x plus 1 at the bottom. There's nothing for it. There's not another x plus 1 on the top, so that's why it's a VA. And when we set x plus 1 equals to 0, we get a VA at x equals negative 1. All right, there we go. Moving on. Now we are going to have to do some factoring, which is your guys' favorite. So number 7, we have x plus 1 on the top, but then we have x squared plus 2x minus 8. So we're going to have to factor. So we're going to make our x factor. Negative 8 goes on the top, and that's what we have to multiply to. This positive 2 in the middle goes at the bottom, and that's what we have to add to. So stuff that multiplies to negative 8, we have 1 and 8, we have 2 and 4. Now, because we have to make a positive number when we add, that means our small numbers are negative. So the pair that works is negative 2 and a positive 4. So when we factor this, we have x plus 1. That doesn't change up top. Let's not write this in gray. Over. Now when we factor this, we get x minus 2, using that minus 2, x plus 4, using that positive 4. And now it's factored. Now we need to figure out if we have wholes or VAs. Okay, now do we have an x, so we have x minus 2 at the bottom. Do we have an x minus 2 on top? We don't, so that means we have a VA at x equals, now if we set x minus 2 equals to 0, or we can just use the opposite sign. We get x is equal to 2. If we have x plus 4 at the bottom and we don't have an x plus 4 on the top, that means we're going to have a VA at x is equal to negative 4. Okay, remember you're using the opposite signs. Oh, if you want to set them equal to 0 to double check, absolutely, feel free. I want you to get this right. Okay, so that's our answer. Looking at 8, we have x squared minus 4, and then we have x squared plus 4. So you always want to check if you can factor your bottom. All right, so x squared, that's a perfect square of x. And then 4 is a perfect square of 2. But what's the sign we have in the middle? We have a plus sign. A difference of squares needs a minus sign. So we can't factor. We can't factor this. So when we set this, so there's nothing for us to cancel out. So that means there are no points of discontinuity. There's no wholes, there's no VAs. Okay, if you can't factor the bottom, there's nothing for you to cancel out. All right. Oops. Number 9. Okay, so we have x plus 3 on the top, and then we have x to the third plus 27. All right, so some factoring skills we need to recall is the sum of cubes. So remember, if we have a perfect cube plus another perfect cube, we set this equal to as a plus b times a squared minus ab plus b squared. Or remember our SOAP, same sign, opposite sign, always positive. Okay, and then you just have to remember the a, the b, the a squared, the ab, and the b squared. So x is a perfect cube of, x to the third is a perfect cube of x. 27 is a perfect cube of 3. So when I rewrite this, when it's factored out, we get x plus 3 on the top. That stays over. All right, so I get x plus 3 times, our a value in this case is x, so we x squared minus 3 times x is 3x plus 3 squared is 9. Okay, now we're going to check to see if we can factor our back piece at all. So we get x over, our x, 9 is on the top, negative 3 is at the bottom. So is there any way to multiply to a positive 9 and get a negative 3? Well, let's check. We got 1 times 9, 3 times 3. Is there any way that's going to work? No, there is not. So we can't even factor this. Okay, so that's as far as our factoring has to go. Now we have to figure out if we have a whole or a vertical asymptote. Okay, so is there something on the top that we have, or for a whole, do we have something on top and on the bottom? Yes, we do. Okay, we have an x plus 3 and an x plus 3. So we have a whole, right? It has to have one of each on the top and the bottom at x equals negative 3. Now, we can't factor this, but we have to check to see if we can get a vertical asymptote. Now, to check, what you're going to do is you're going to use something called the discriminant. We did this way back in the day, which is using b squared minus 4ac. Okay, so my b value in this case is negative 3 squared minus 4. My a value is 1, my c value is 9. We get 9 minus 36, and that equals a negative 27. So that means we're going to get an imaginary number. So we don't have a vertical asymptote anywhere. So we only have a whole at x equals negative 3. All right. Looking at number 10. Okay, so let's look to see if we can factor the top, because it's 6x squared plus 11x plus 3, so it might be factorable. So we're going to look. So we have to do the front number times the back number, so we get 18, that's what we need to multiply to, over our plus 11 is going to be what we add to. So stuff that multiplies to 18 is 1 and 18, 3 and 6, 2 and 9. So 2 and 9 work. Okay, but now let's look at the bottom. Let's see if we can factor the bottom. So we have to multiply to 5, but add to 4. Well, stuff that multiplies to 5 is 1 times 5, and that's it. Now, is there any way we can multiply to a positive 5, but add to a positive 4? Well, if I do positive 5 and a positive 1 here, when I add those, I get 6. If I do a negative and a negative, negative 1 times negative 5 gives me a positive 5, but when I add those, that gives me negative 6. Okay, if I do negative 1 and positive 5, well, when I multiply those, I get a negative 5, so that's not going to work. So that means that means it can't factor. Okay, now we're going to check using if there's going to be any points of discontinuity. we're going to check using our discriminant function. Okay, and again, that's from number 9, so we're going to check using b squared minus 4ac. If you get a negative number, that means you're only going to have imaginary solutions. So we're going to check, and we don't want imaginary solutions. So we have b is 4, so we have 4 squared minus 4 times 1 times 5. 4 squared is 16, minus 4 times 1 times 5 is 20. Well, this gives me a negative 4. So if I have a negative answer for my discriminant, that means we're going to get imaginary solutions. And can we use imaginary numbers in points of discontinuity? No. So that means we're going to have no points of discontinuity at all. All right. So your homework is your homework is the 7.2 day 1 worksheet. Okay. Now again, before you guys log off or exit or whatever it is that you do, if you can't factor it, you're going to use the discriminant, which is b squared minus 4ac. Okay. If it makes a negative number, that means there is not a point of discontinuity. Okay. All right. I hope you guys have a wonderful day. As always, please email me with any questions that you have, and I'll talk to you next time.